record it. And then I will share my screen. Okay, so today the first new concept is about decision tree. Okay, and for decision tree, it says it's also quite useful for classification. And a lot of time you also see the abbreviation like ID3. Okay, so what it means is iterative dichotomizer 3. And this algorithm is invented by Ross Quaylen. Okay, and it's going to be used to generate a tree. Okay, so we are going to use samples, and based on samples features to generate a tree. So that's a major thing. And this decision tree, or we call it ID3, it's quite useful in machine learning and natural language processing domain. So it's quite useful for natural language processing domain, okay, because it's use a tree structure and based on the features. So this is one of the main feature. And then later on, another research or other researchers and Quinn also did extension for ID3, and it's called C4.5, okay, in decision tree domain. And what's the next? Let's take a look this diagram. So in this diagram, and we see it's a tree structure. Is it a tree? And here, based on, because it's a tree, so you have a lot of nodes. Is it? So this is considered as a root node. And from this root, you have two branch. Is it two child branch? So for over here, basically, it's some kind of condition. Say, oh, do you have work to do? Is it? Your answer can be yes or no. Is it? If it is yes, okay, to go to the left branch. Then you say, okay, you're going to stay at home. And if you don't have work to do, then it's go to the right branch. You say, okay, then you need to check Outlook, is it? And this Outlook, basically, it's also a node, is it? And we call it internal node, okay? And for this Outlook, then you need to check what's the weather condition, is it? So there are more branches. So it's based on, okay, if the weather is sunny, if it's sunny, oh, you say you can go to beach, okay? And then you already made your decision, is it? And so that's, for this node, we call it a leaf node. Why we call it a leaf node? Because it doesn't have any more branch out from this node. So this is a leaf node. And for the beginning node, we basically, there is no other a branch leading to it. So this is a node, we call it a parent, we call it a root node. And compare the work to do node and the Outlook node. The work to do node is a parent node regarding the Outlook node, okay? And based on your answer, okay, if it's raining, then you see you may want to check with your friend. So you go to another branch, is it? And the friend's busy, this is another node, then you're going to check because depends on if your friend is busy or not. Then you can see what you can do. So this gives us a structure of decision tree. And based on this structure, we just see, and for decision tree, basically it's pretty good interpretation, is it? So you can interpret some of the decisions based on conditions, is it? So it's quite good at breaking down data by making decision based on asking a series of questions, so based on the conditions. So that's decision tree. And decision tree, basically, what here the major thing is, it's a white box, okay, type of machine learning algorithm, because you can see the tree, is it? And because you see the tree of the internal node, we also see. So basically, you also can see of the internal decision-making logic, is it? So compare decision tree with another kind of very popular popular machine learning approach we call neural network. And neural network, then all of the decision is completely dark. So you won't be able to see how the decision is made. Is it? So for neural network, it's a black box type of algorithm versus the decision tree, okay? And also here it says the decision tree, its training time is also pretty fast to compare with neural network. Okay, but it says a time complexity of decision tree. It's a function of the number of records. So it's based on your sample space, is it? And also it's a number of attributes, is it? Because the attributes will give you the condition to determine which branch you're going to go. And decision trees has said is also distribution free and non-parametric method. So it does not depend on probability distribution assumption, okay? And the decision tree, it can also handle high dimensional data with good accuracy. So those are the features of the decision tree. And the decision tree, some other major features and advantages for decision tree is it's a transparency. Why we say it's a transparency? Because you can see all of the internal nodes, that internal decision and the related decision. And also its computation cost compared with other algorithms, it's also low, etc. So it's quite useful. So one of the major features for decision tree used a lot in machine learning is it can be used for exploring data. Okay, so before you apply some algorithm, yeah, so you can basically here is you can use decision tree to do some pre-manipulation, is it, about all of your features. And after that, then you can apply some other machine learning algorithm. So this is one of its major feature and another major use. And also, as the decision tree also quite helpful for check the quality of engineered feature. So here, once again, like I just explained, it's because it's good for the features, is it, to pick out the feature for explore the data. And then you can identify the most relevant feature by visualize the resulting tree. Later on, we are going to see our examples, okay? So one of the major things here for decision tree is it will be quite good for exploring features, okay? And here it says the downside of the decision tree is it's tend to overfit. And do you still remember the overfit and the underfit concept? This is also important. And overfit, that means it has what? Has a higher variance, is it? Underfit means, generally speaking, it has a bias, is it? So over here it says decision tree tended to have overfit because you need to make a lot of decisions based on a lot of conditions. So that's why it's tended to overfit. And because of the overfit, so it's not good to get the relationships between features. Okay, not like other algorithm. You can get some relationship between features. Is it like a linear regression? And normally regression can be pretty good used for find the relationship among the features. Okay, and then it says later on we're also going to see the random forest. And the issues with decision tree is that it can be kind of lessening by random forest. Okay, so that's a decision tree. So with decision tree, there's a couple of terms that we need to understand before we go to its math expression. This is starting at the tree root. We already know it's the top node, okay? Then you're going to split data. So here we are going to split the sample data, okay, on the feature. So it will be split on the features. And how do you split? So there are a lot of ways you can split the data, is it? So the rule you're going to build the tree is based on the largest information gain. And we have a formula for information gain. So just remember it represents IG, okay? It's information gain. And for decision tree, because you want to build the tree, is it? So it's an iterative process. You're going to repeat the splitting procedure. So basically you have initial sample space. Then you're going to split your sample space based on the feature to split it until you reach the leaf node. Then your tree is done, okay? And then because of this, it can result in some deep trees, is it, with a lot of nodes. Then that's the reason why it can lead to overfitting. Previously, we discussed it, overfitting, is it? So to prevent overfitting, you can do some pruning of the tree, okay? Set the limit of the maximum depth of the tree so that your tree won't go too deep. Okay, then the next part is regarding some math background about a decision tree, because we are going to do split. And the split is based on what? It's based on information gain. And you're going to maximize the information gain, okay? So what is information gain? And here we also have the objective function. And previously we learned cost function, etc. So there are different kind of function. So for this information gain, etc., this information gain. And here what it shows is, it shows D and F, okay? And here it says F is a feature you're going to split, okay? And the D represent data set, okay? And the P, so here you have the DP. So DP represents the data set of the parent. Okay, and then over here you have DJ, is it? And this DJ represents the J's node, the child node. Okay, and what I represent the impurity measure. Okay, and N represents the number of samples. Okay, so this is the general expression about the information gain. And it explains what is information gain. So information gain basically is just a difference between the impurity of the parent node and the sum of the child node impurities. Okay, so the lower the impurity of the child, the larger the information gain it will be, is it? So that's why you always try to, whenever you do split, you try to maximize in information gain. So that's our goal. And then next, let's see. And here to maximize information gain, and for simplicity, what we are going to discuss, and also to reduce the search space, mostly, and including the sklearn library that we will use to do the decision tree learning. It implements, it do the binary decision tree. So it will not have more than 2 branches. So each tree will only have 2 branches from a node out. And because we are only going to use binary decision tree, so the information gain representation, its expression then expressed like this. So this is parent node's information gain, okay? And it's from its impurity, the parent node itself's impurity, minus the left child's impurity and the right child's impurity based on their share. So that's the expression. Okay, and then let's see, how do we measure the impurity? Yeah, the splitting criteria. And there are multiple ways. So generally speaking, there are 3 ways to do the impurity calculation. There is one we call it a Gini impurity. So normally you represent as IG, so Gini. The second is entropy. Okay, so in information system, you see this word a lot, entropy. Okay, and in this case, so this is the second way to calculate information gain, and the third way is classification errors. So it's IE. So we are going to take a look of them. And for the entropy, so the one we just discussed, how do we calculate the entropy? Is it, see, the entropy calculations is for non-empty class. So it's use probability to do the calculation, okay? And here says this probability pi and slash t, is it? It says it's a proportion of the sample belong to certain class C, okay, for a particular node. Okay, so you remember we have the node, is it? The node is going to do the split, is it, by split. So within the node, you have certain number of samples. So N is a number of samples, is it? And over here, what it says is just the sample belongs to certain class for a particular node. So for this node, how many of them is it belong to this specific class? Is it? So that's what it means about this probability calculation. And for the entropy, so it's the summation among all of the classes. So from the first class to the last class, because you're going to do classification, okay? You want to see, okay, how many class, how many group you're going to have for your sample space. And the entropy criteria is just as try to maximize the mutual information in the trees. Okay, so that's about entropy. And then next, let's take the Gini impurity. Okay, for the Gini impurities, they can be understood as a criteria to minimize the probability of misclassification. So the probability calculation is the same as what we just saw from entropy calculation. But the formula given like this, is it? So the probability for the samples belong to certain class C, is it, at that specific node in your tree, okay? And this is similar to entropy. The Gini impurity is maximum if the classes are perfectly mixed, okay? Then you will get the most. And this is in practice, basically Gini impurity and entropy typically yield very similar result. So it's often not worth spending much time evaluating using which one is over the other one, is it? So they give the similar result. Okay, the next one is the third one, is it? Because we try to do the maximizing the information gain. And information gain, there are three ways to calculate information gain, okay? The third one is classification. So for the classification, then the algorithm, the expression given is the gain I is 1 minus the maximum, the maximized one of the probability among all of them, etc. So it says this is a useful criteria for pruning, okay? But it's not recommended for growing a decision tree. So if you grow your decision tree, you better use either Gini or you use entropy. So that's the point. But when you try to do pruning, then you can pick the classification error. So, and why we need to know this is because when you apply sklearn to do the training, you need to plug in the information gain, etc. So at that time, you need to make your decision among these three, which one you need to pick, okay? Okay, the build decision tree says the deeper the decision tree, then the complex the decision boundary is going to become. So it will result in overfitting, okay? So feature scaling for this algorithm, it's not a requirement, not like our algorithm. Is it like SVM? You still need to do scaling, is it? For perceptron, you need to do scaling, is it? For logistic regression, you also need to do scaling, feature scaling. And previously we discussed the feature scaling uses standardized, etc. That's the use a normal distribution to do the calculation, to do the feature scaling. Okay, so just remember also, this is also very important, and we keep repeating to mention it. So in machine learning, feature scaling is important, but not true for decision tree. Okay, not true for decision tree. Okay, because the major one of the major application for decision tree is feature engineering. Later on, we can see, okay, it's a feature explorer. So that's one of its major use for decision tree. So that's why it says, because it's majorly pick feature, and we also see it's based on what? It's based on the probability, etc., of certain number of your samples belongs to a certain class. So feature scaling is not important in this case. And also in sklearn, we were also seeing our code. It also allows you to export the decision tree. So basically, we can also visualize our tree. Okay, so that's why we see it's a transparency, is it, for decision tree. It's a white box one, not a black box one, like a neural network. You don't know all of the intermediate learning procedures. And in decision tree, you will know of the decisions it make intermediate. Okay, and then decision tree, because the downside for decision tree is what? It's overfitting, is it? And it's overfitting, so there is a way to mitigate the overfitting is you can combine, we can combine multiple decision tree together, etc. And we call it to build a forest. So we call it a random forest. So you can use a random forest to mitigate, to relieve the overfitting issue. Okay. So it says random forest, basically this learning algorithm, it's an ensemble of the decision trees. So it's a group of decision trees. So you put them together, etc. So that's why we call it ensemble, okay? So this is also a key word in machine learning. You also see that a lot, ensemble. And the idea behind the random forest is that you average multiple decision tree, okay, that individually may suffer high variance. And then you can build a more robust model that have better generalization performance and less susceptible to overfitting. So less sensitive to the overfitting issue, okay? And because you're going to average them together. So that's random forest. And it says random forest can be summarized in the following simple steps. So you can draw a certain number of the samples from the original data, okay? A random is that you may pick with replacement. Okay, so we call this a random bootstrap sample of size. So you don't need to have all of the samples, okay, in your for your random forest. So you pick a certain number of them from, then use that certain number of samples. You grow a decision tree, okay, and grow the decision tree is that at each node you random select a feature, okay, but when you select feature, you don't do replacement. And then you split the node, use the feature, okay, to do the best split, okay, and using maximize the information gain. And then says you can repeat this previous two steps. And after that, you can aggregate the prediction by each of the tree and to assign the class label and using the majority vote, okay. So you have, suppose you have 10 trees, is it? And each tree based on different samples, is it? And different features you pick to do the classification. Then when you aggregate them together for certain testing sample, you can let it predict. Maybe among 10, 8 of them predicted as class A, and another 2 predicted as class B, is it? Then in this case, it says you just follow the majority vote rule, okay? And it says combine the multiple tree decision tree via random forest, and the random forest doesn't offer same level interpretability, is it, as decision tree? Yeah, of course, because you aggregate them together, is it? But the big advantage is as you don't need to worry about choosing good hyperparameter values, is it? And also we don't need to prune the tree. We don't need to worry that, okay? And but the major thing you need to make your decision is the number of trees you pick. That's going to be important. So the number of trees you're going to pick, that's important. So it says the larger the number of trees, the better the performance. And of course, is it? But your computation cost is going to grow up, okay? And also the size of the bootstrap samples and the number of features. So those are some important parameters when you do optimization for your random forest. And it says in most implementations, says the size of the sample is chosen to be equal to the number of samples in the original training set, is it? And can provide a good bias variance trade-off. And for the number of features at each split, is that you want to pick a value that's smaller than total number of features, is it? But it gives us some recommendation, okay? So a good recommendation is you take a square root of your total features. Then that's the subset of the features for each of the tree, okay? So this gives us the general idea about decision tree. Let's see how I bring it back. Oh, I need to stop sharing. Okay, now I can bring it back. So I'm going to pause a little bit. Okay, so we just discussed the decision tree, is it? So Devon, you ask what is a random forest? So now do you understand what is a random forest? After we explain the random forest. So random forest is not a single tree, is it? So it's you aggregate multiple trees together. So you have multiple trees. So from a single sample set. So from one sample set. So from all of the sample sets, is it? You pick some number of samples to build a tree, to build a single tree, and with a subset of features, not all of the features. And you build multiple such trees, and then aggregate them together. Trees together. So that's called a random forest. So when you make a decision about the class, you use majority vote. Yeah, exactly. Yeah, exactly. So random forest, each time when it build, it pick a subset of the features, not all of the features. Yeah, exactly. Any other questions? And if there is no other question, we are going to resume recording. Okay. So what we just discussed is regarding the mass calculation of information gain. So we just see the simple numerical model, okay? So simple numerical model for information gain. That's what we just discussed. And once we understand this, and now we can go to take a look, how do we do the decision tree and the random forest in sklearn. Okay, so next, we'll discuss in sklearn. So I will, oh, I forgot to record that part. So if you study what we just discussed about the tree graph, you can see it quite clear about the decision tree's intermediate step. And we can go back to take a look at our code. Okay, and here, if you take a look at this picture, is it? This picture also shows us the 3 classification. And if you take a look at this cluster 1, this red color, of this red color, if you take a look at this diagram, it's petal width, is it? It's less than that 0.75, is it? So, and if we go back to take a look at this tree structure, is it? For this tree, the very top part, we said, let me do this. No, I cannot. So probably let me, otherwise I cannot show everything kind of. Let me do the annotation. If we take a look at this tree, you see the parent node, the first split condition is based on petal width. This petal width is less than 7.5, is it? And it has all of the branches go with settlers, is it? And if we go back to take a look at our code, look in this diagram, is it? We also see this part. It's less than 7.5, is it, for the petal width. So compare the result, we can find that both look pretty good, pretty match, is it? So that's why we see decision tree can give you a very good feature selection. So in that case, it looks like the petal width is pretty good at pick all of the flowers that belongs to settled club. And then let's go back to our coding. So that decision tree pretty good at pick out of all of those settled flowers, because this cluster is all belongs at 0.75. Okay, so that's regarding the visualization of your tree, okay? And the last one we are going to take a look at is random forest, okay? And regarding random forest, it's also pretty straightforward. You first need to create a random forest model, the object, so you specify the criteria, it's Gini or it's entropy, is it? And here 25 means how many trees you want. So in this case, you said, okay, I want to treat 25 individual decision tree, okay? And the last one, the number of jobs, so it supports parallel processing, okay? Because in case, if your calculation load is quite large, then you can apply parallel processing. And after that, then you can just do fit, is it? And do the fit, and you can see the result split is quite good. So it's more detailed of the classification. So basically, that's the general overall about this new algorithm that we learned. So today we mainly learned decision tree, okay, and random forest. And the decision tree, and like I explained the tree diagram, you can see it's pretty good for, so decision tree is good for feature engineering. For you to pick out the features. After you pick out the features, then you can do more training using some other algorithm.